Welcome to this class on biomedical instrumentation. In this video, we will look at amplifiers. What are some of the critical characteristics of the amplifiers? For example, bandwidth and input impedance and output impedance. What is the need for us to have an amplifier? Because if you are having a signal that is having low amplitude, you are interested in increasing the amplitude of this signal, or you are essentially interested in increasing the signal strength. So these amplifiers are systems, usually electronic devices, that increase the amplitude, enhance the amplitude or power of the signal. In biomedical instrumentation, we are interested in increasing the physiological signals that are very weak. For example, in the case of EEG, you are going to have amplitudes that are in the order of microvolts. But usual systems, usual display systems and measurement systems can only measure up to volts. So that means that your amplifier should have at least a gain of 10,000, for example. So amplifiers are absolutely required or indispensable for enhancing the amplitude of these signals to an understandable human intelligible level so that we can process, display, and understand. A critical component of this amplifier is the so-called operational amplifier. Operational amplifier is the essentially represents an IC or an integrated circuit device that is widely used because of its properties, desirable properties. What are these desirable properties? High gain and relatively high or good noise characteristics. So these op-amps are high gain DC differential amplifiers. So if we understand how the op-amp works, this is key to understanding and to design good signal processing or amplification circuits that also reduce noise. A key characteristic of an amplifier, for example, is the gain. This is essentially the ratio of the amplitude of the output to the amplitude of the input. That is, what will be the output of the amplifier for a small input? That is, earlier we looked at it as sensitivity. Here we call this as amplifier characteristic gain. In an ideal op-amp, the gain is infinite. That is, even if I give a value that is infinitesimal, nearly small, nearly zero, so small that it is nearly zero, my output will be infinite. Practical op-amps don't have that much gain, but it is possible for us to have gains above 10,000, for example, at least in a multi-stage configuration. We will look at all these details in future classes. Having high gain essentially means that we can have relatively precise control over on the overall circuit design. So that when we use negative feedback, I can have high control. For example, we can have high gain amplifiers, high gain low noise amplifiers in a situation like EEG, because the EEG signals are of the order of microvolts. Or we can also use current to voltage converters that can be used to have extremely or very high gain. So another related characteristic is the characteristic of bandwidth. What is bandwidth? Bandwidth essentially is the range of frequencies over which the amplifier can produce high gain or can effectively amplify the signal without increasing the noise. So what is the range of frequencies in which you will have high gain and relatively low noise? This is called as the bandwidth. It is possible for the signal to have some amplification outside of this bandwidth, but that is not entirely a desirable range, for example. For example, an ideal op-amp will have an infinite bandwidth, meaning it can amplify signals starting at DC to very high frequencies, but practical op amps don't have, infinite bandwidth. That is, all amplifiers have finite bandwidth. It says all amplifiers have infinite bandwidth. That's actually wrong. All amplifiers, all practical amplifiers actually have finite bandwidth. Usually, we are interested in having wideband amplifiers, those that are designed for broad range of frequencies, critical for applications like ultrasound, for example, where echo signals are modulated over carrier frequencies requiring significant amplification. So that means I am interested in having a wide band. I am interested in having an amplifier that is going to produce high gains over a relatively large range. Then you have input impedance. This is the opposition. This is the resistance or the opposition that an amplifier presents to the input signal flow. Why is this important? So that we can avoid loading. We already discussed this briefly. An ideal op amp has an infinite input impedance. Infinite means that is absolutely no current ever goes through the op amp. Is almost all the current goes through the resistor connected to the op amp. So essentially, you want to make sure that the amplifier does not draw current from the signal source, preventing what is called as loading. That is, the amplifier does not alter the signal that it is trying to amplify, that it is trying to measure. Another necessity is the low output impedance, because you are interested in loading, you're interested in driving a load without a significant reduction in the output signal. So you're interested in having a high input impedance, you're interested in having a low output impedance. Practical op amps have very high input impedance, but not infinite. Biomedical systems or biomedical amplifiers, biopotential amplifiers usually have input impedances higher than 1 gigaohm or 10 gigaohm, for example. So we will proceed with the biopotential measurement, filtering techniques, and noise sources and reduction techniques. What is signal processing? Signal processing essentially implies manipulation of signals, so that we can extract whatever we consider as a useful information to enhance their quality. That is, essentially, we are interested in extracting useful information from the available information so that we can use it to make decisions, so that we can prepare them for subsequent analysis or display, so that the medical professional can make a decision. It's absolutely critical in biomedical instrumentation, because there is always some noise present, and there is also sources of artifact. Please Google about the difference between noise and artifact. Okay? These obfuscate or otherwise confuse or otherwise change the true physiological signal. So what you're measuring is something, it is representing an underlying ground truth, underlying physiological signal. You are interested in measuring this with a relatively high degree of confidence. Now, advances in signal processing techniques have essentially enabled us to improve the capability of the medical devices. Another related concept is the source of noise. What are the various sources of noise? What is noise? Noise is essentially anything that is not wanted, that interferes with the desired signal. So if you are desiring ECG, for example, any movement of the muscle may be noise. But if you're measuring muscle activity, then the movement of muscle is essentially signal. So depending on what you are interested in, what you are desiring, anything that is not desired is noise. This leads to unwanted inaccuracies in the movement. This is noise. What are the sources of noise? There are various sources. One source is physiological noise. That is, like I already said, if you're interested in measuring ECG, EMG is noise. But if you're interested in measuring EMG, ECG can be noise. For example, For example, depending on which one you are interested in, the other one is noise. Then there is environmental noise. For example, as I'm speaking, there is a fan whirring. That is an environmental noise. You are interested in listening to me, but not necessarily the fan whirring. That is if you're interested in listening to me. But suppose you're interested simultaneously, you are listening to your mom speaking, or you're, let's say, you have somebody else and another loud one who is interested in having a conversation with you, then the lecture that I'm giving is noise. Depending on what is desirable, the undesired one becomes noise, then the desired one becomes signal. So there is environmental noise. So there is an unwanted signal that is produced in the environment that interferes with the desired signal. You can't remove this noise. In many cases, almost all the cases, most of the cases, it is next to impossible to remove environmental noise. For example, you're teaching a class, there is some construction activity that is going on, that is making this sound of type of noise, some sound. Now, that is noise. But if the student is only interested in listening to me, then it is noise. But if the student is not interested in listening to me, then, well, then, then my words are noise. So remember this. There are other sources. Instrumental noise. This is noise that is generated by the electronic components. Your measuring device has an electronic component, and that by itself generates noise. The components within the measurement system itself causes noise. For example, shot noise or thermal noise. Then there are artifacts. Artifacts are not exactly noise. There's a slight technical difference between them. Please do check what's the difference between a noise and artifact. This is, for example, movement artifact is caused by the movement of the patient. A live person will always have movement. Right? These are the different types of noise and artifact. Now let's look at the various subtypes of different types of noise. In the real world scenario, various sources of noise exist. For example, this can be this can happen due to environment, this can be power line interference, this can be due to thermal interference, and so on and so forth. If we can describe what the spectrum of this noise is, then it may be possible for me to filter them out. But not always. In some cases, it may be possible for me to filter them out. For example, thermal noise. This is also called as the Johnson-Nyquist noise. This is caused due to random thermal agitation of electrons in the conducting system. So this has power density across all frequencies. It's also called as white noise. So this Nyquist theorem essentially governs this thermal noise. Then you have what are called as 1/f noise. This is also called as a flicker noise. And in this case, the power density of this noise varies as the inverse of the frequency in the low frequency range. This is usually seen in semiconductors due to carrier fluctuation. Then the so-called resistors. This is also seen in resistors when current flows. This is called a 1/f noise. This is also found in physiological signals for like heart rate fluctuations and the very low frequency drift. This is considered part of the 1/f noise. In physiological systems, sometimes 1/f fluctuations may contain meaningful information. So it's not always noise. Sometimes 1/f is essentially representative of a physiological phenomenon in some cases, although not always. So that means depending on the situation, you may or may not classify the 1/f phenomenon as a noise, and sometimes you may actually classify this as the signal of interest. Then you have interference. Something is happening outside. Let's say I am speaking in a particular room, my family members are speaking in a different room. For example, you are speaking on the phone with your friend. Your family members are speaking on the phone from the different room. For you, their speech is interference. For them, your speech is interference. This is external physical or chemical sources that are causing this interference. Common sources are, for example, power line noise, power line interference. This is always there because you cannot have an electronic system without a power line. So as soon as you start a measurement system, there is always a power line, and there's always a noise or interference that comes from the power line. And also in the biomedical situation, there might be other bigger electromagnetic devices. For example, in the ICU, there might be multiple instrumentation systems. For example, fluorescent lamps that may have a what is called as a choke, which is essentially a coil that is an electromagnetic device. Then mechanical vibrations that happen from machines that also cause noise. So the spectrum of interest depends on the source of the noise. Remember, you can filter out noise only if you know what is the spectrum of the noise. If you don't know what the spectrum of the noise is, then you actually cannot filter it out. Sometimes the signal of interest and the spectrum of noise will be overlapping. In that case, what will you do? In that case, how will you remove that noise? Sometimes interference may appear as discrete peaks at resonant frequencies. In some cases, it may be possible for you to remove them. In some cases, you will have to live with these noise sources. Then you have what are called as artifacts. What are artifacts? For example, a common form of artifacts is the movement artifact in EEG, for example. Blood is flowing and causing motion, causing movements in the head. Electrodes are moving because of this blood flow, for example. So depending because of these movements, measured potential changes. This is called as movement artifact. This may be due to skin potentials, change in the skin potential, or change in the electrolyte properties, electrolyte interface changes. This is not so easy to filter. This is actually quite difficult to filter because in this case, for example, it has frequencies that are overlapping with the physiological signal of interest. So it's called as the artifact. How do you reduce this? By using non-polarizable electrodes. We'll discuss this in future classes or future videos. Or we can reduce skin potential. We can abrade, or we can use puncture. We can use sandpaper to abrade and then improve the skin potential value so that we short circuit the stratum corneum, or the topmost layer of the skin, for example. Other specific example, for example, in the pacemaker pulses, if a person is having a pacemaker and you are measuring that person's ECG, then the pacemaker pulse is a significant source of noise when you are monitoring ECG in a patient who is having an implanted pacemaker, for example. Now, these values may be quite high when compared with typical ECG signals. ECG signals values are in the order of units of millivolts. Sometimes you will have the pacemaker values that are as high as several tens of millivolts. With this, we'll end this segment. We'll continue this discussion in the next segment. Thank you.